Jonathan. Samuel. Rihanna. Bobby. Branson. Jacob. The bridge should already be under control. Check if it's consistent with this other paper. Check. Code your answer. Samuel, that's not the right one. Those are right. It's because I know it's like I don't know. So What's that? What? One. Christopher. Oh, he's on here. Anyone else not having your exam back? Okay. Because it's to that you let your energy. Let's check the rating on the test paper. Talk about it when you are not sure. I see Alexandria. Johnson. About. Oh, I just. No. All right, let's how to determine the formula. So basically you can see it goes positive, negative, positive, negative, positive. So the formula is, there has to be a -1 to the power of, you see -1 to the power of, instead of n, we have an I in here. So let me copy and we can talk about it. Many of you already have the right formula, but I just want to explain possibly one type of reasoning. There's a lot of way we can analyze this. Different people tend to follow different routine, but because of sign are rotating, I know that it's a summation of, there has to be a -1 to a certain power. This was using I, all these choices are using I, so we're just go I, and here we can go I -1. So that is part of the factors, part of the things that we multiply. And then we realize what we are doing. 4 become 1, 1 become 1/4, 1/4 become 1/16. You see there are 1/4 multiplied to it. So we know that the other number that we gotta multiply is 1/4. So instead of -1, we can go -1/4 to a certain power because we were repeated multiplying the 1/4 over and over. And then another thing is, if the formula is if we got this, and then we look at what we have to do as the first value, and it won't. If I start with 1, like all these are having, I start with 1, and then how does it look like? It would look like when I equal 1, you go 1. I 1 minus 1 is power 0. Any number to the power 0 is 1. The second one is when I equal 2, then you have -1/4. And then I equal 2, I equal 3. 3 minus 1, I equal 3 is -1/4 to the power 2. So it's a positive 1/16. And then we go one more. There's 5 terms. The highest number will be 5. So I from 1 to 5. Since there's only 5 number, so the next one is -1/64. And the next one will be I equal 5, so that would be 64 times 4. I think that's for sure the number is going to be positive what is it, 1/4 to the power 4. So that's how it looks like if we don't change or multiply additional number. And you can see we're not starting with 1. This is when you start with 1, but we start with a 4. So one possibility is to multiply the whole thing by 4. 4. That means we're gonna multiply 4 to the whole summation. This is summation of 5 number using an algebraic formula to present the summation. This 4, you can bring the 4 to the outside of summation notation, or you can bring them to the inside of the summation notation. So with all these considerations, I think the correct method will be the B. Here. The B, the effort is to guarantee the first number is 4. If you look at the A with, it will start with 5 instead of 4. Because when I put a 1, I'm 1 minus 1 is power 0, negative 4 to the power 0 is 1. Any number to the power 0 is 1. So when I put a 1, you have 1 plus 4, which is 5. And we're not starting from 5, starting from 4. So A is not right in a way is looking at the whole calculation as a summation instead of multiplication. So we cannot add a 4. We have to multiply 4. So A is wrong in the way of analyzing relation factors. C, you can see it was at the beginning, that was the first formula of the writing. If you have C, that's before I multiplied the 4, and you see we start with 1. So C has the wrong initial term. The first term cannot be a 1. And then D, the problem is it has the right value, but D does not alternate. There's no negative 1 full power. Therefore, in D, all the term will be positive. So D will be like 4 plus 1 plus 1 fourth plus 1 over 16 plus 1 over 4. So D doesn't have the alternating signs. The correct answer should be B. I hope that kind of explains all the reasoning when we're making the choices. You should already have your test paper. Recorded all the answers. Do you have any questions now that the paper is in your hand? Question. I posted the overall data for the whole class. We are 35 students in the class, 29 of you took the test. If you haven't taken it yet, you're welcome to schedule a makeup exam from the testing center website. I'll send the exam to the testing center. But please make sure to let me know what was the date and what they do require the exam to be at the testing center. Since the testing center do not have our exam, so make sure that we communicate well enough so that when you go take the exam, the test is already there. You can see the average of the entire class is 82. The maximum score is 102 because I added actual credit for the homework. And that means that without the actual credit, our highest score is 98. And those are the history structure data. We do have a few. The spread is represented by standard deviation 12.9. The standard deviation of the data. So you can see from student to student, we have very different situation, and the best thing is to compare your own homework with a exam. If you have been working on the homework a lot of time and still didn't do well on the exam, maybe we could work on the one timing. Maybe it took me a longer time when you do it homework at home, but now in class you're required to finish in limited time, so the time might be an issue. Another thing is I am allowing you to use formula if you have one. Maybe you didn't have it prepared, so that sometime before the class, if you don't feel like you're prepared, it affected your mentality. You take the exam, you didn't perform as you expected. And we try to think of ways to improve. You're welcome to retake the exam if you feel like you can do better. So after finishing your homework, maybe you can Who use it or? So. The school is B. So normally after them, I will try to, I'll try to survey the class. Number one, that you have your test in your hand. I'm not sure about the level of difficulty. I selected the question out of the homework. You feel like the test is harder, expected, or easier? Let me know what you think. And we did similar things after test one. This is a survey, helping with inputs, a better idea of and your name, see if your response is recorded. Okay. So, assuming that's all the responses. Okay, so, most of you had the number with 13 student in the class answered A. The test is as expected. Three of you answered harder than before. And this time nobody felt like it was easier than expected. Okay, so that's what was found, a perception of level of difficulty. And then there's also homework. So I wonder how many of you did do your homework on chapter 7, that as a result of homework, it could be related to our test performance. You submit yours?
Yeah.
Okay. All right, so 21, so that I guess most of you, when you're attending class regularly, you did finish most of your homework. That's good. All right, I don't want to have too many survey in here, but overall, that's what happened on test 2. But then again, unless it's the end of semester, which we are running out of time, we're still in the middle of semester. It's possible for you to retake any of the past exam. It is possible for us to reopen any homework that you feel like you can do better. So, so try to rethink all your tests I've done. Maybe you did better on test 1, not so good on test 2. Maybe you did good on test 2, but now so good on test 1. But if you had, you're willing to retake any of the tests, well, you're welcome to mention that already. Right. We have already moving on to chapter 8, and we're studying sequence and series already. And today, my hope is try to finish 8.2, try to finish 8.2. Then tomorrow we'll move on to 8.2. We're a little bit slower than what I anticipated on the schedule, but the schedule each semester try to allow a little bit of space for flexibility, so it's okay to be a little bit behind. The schedule was over here under C. We're just finishing spring break CEC. I plan on moving up to 8.6. Obviously, we're not there. We're 8.2, so review section. And I hope to have test 3 on the 26th, which will be next Thursday. I don't know if we can. We have 8.2 right now, so we have to finish 8.3, 4, 5, and 6. So you two we probably won't be able to finish all the sections for chapter 8. So very likely I'm moving the test to the week after. So we'll probably move the test from March 26th to April 2nd. So that's fine. We have the file ready. We're going to review what we did before the break. So 8.2, the title is infinite series, and we probably shouldn't start from the beginning. Prime. All right, so infinite series is really adding infinite many number and what was it called summation. And we were studying different type of series to say some of them can have a finite sum, some of them don't have a finite sum. We started with the example. This is the example that we did at the beginning. We have a sequence and also add all the number in the sequence. A sequence is a list of numbers that could have some pattern. A series is a summation of all the numbers in the sequence. So that's why sometimes we call it a series, sometimes we call it infinite series. Or infinite being omitted sometimes because series, the word itself indicated infinite sum anyway. Right, so we start with this example and look at the partial sum, adding one number, adding two number, add three number, add four number. And we observe some pattern and realize the summation of the first n number has a formula 1 minus 1 over 2 to n. And then the limit value when n goes to infinity, the limit value equal to 1, which means if we add up the infinite number in this sequence, we have a total summation of 1. Right, that's the summation of all the terms in the sequence. So we define the terminology of the infinite series or a series, and we define the partial sum as a sequence, a new sequence. So an is the sequence, but adding the first n number in that sequence is s of n. S of n itself is also a sequence. If this sequence have a limit, then the original series converge. If S of n does not have a limit, then the original series diverge. So those are definitions about converge and diverge of a series. So according to what we said, the series of a summation of 1 over 2 to the power n converge and the infinite sum equals 1. And we have a couple of examples on proving, how do we prove a series diverge? And there are two different situations. The first one is when the total summation equal to infinite number, equal to infinity. The second scenario is when the partial sum is alternating. And that's why the infinite sum diverges. There's two different scenarios. The first one, we look at the partial sum of adding the square number. 1 square plus 2 square plus 3 square plus n square. We have a summation formula. So it's actually a useful formula later on. Now this s of n when go to infinity equal to infinity. Therefore, the infinite sum equal to infinity. Therefore, diverge. So first situation when diverge happen to a series. A second situation is when the partial sum looks like this. This is an individual number in the sequence. This is a partial sum. So the partial sum is a sequence that goes 1 0 1 0 1 0, just alternating, and therefore there's no limit. S of n it has no limit, therefore the original series diverge. This is the graphic display of the sequence and this is two sequence. One sequence is the original sequence an. The other sequence S of n, we're drawing it on the xy plane. The x value are the n. A1, A2, A3, so 1, 2, 3 being the x value, and then the original A and the y value, so we're able to plot it. The part of the reason that we plot things is to visually identify the tendency of the sequence, right? So both of them are diverging, or approaching infinity. And then the second example is alternating. The original an is alternating, original sequence is alternating, the partial sum sequence is also alternating. All right, and one of the special situations in this section, we study geometric series. Geometric series is the one that we could have a formula for the total summation. We got this formula. If you have a summation of r to the power n, then we have a formula for the partial sum. I haven't really changed it. S of n equal to 1 minus r to the n, and not n plus 1 from r to the n, divided by 1 minus r. And then when n go to infinity, if r is a small number, so r to the n, r has to be less than 1. R to the power n would go to 0 and to infinity. So then the actual infinite sum will be 1 over 1 minus r because the minus r to the n approach 0. That's the one that we actually have a formula for its calculation. And then I try to prove it. This is we went over this already. You write down the partial sum. It's the summation of the first n number because there's a 1. Okay, so the last one is not r to the power n, it's actually r to n plus 1 if you're adding n number in the sequence. So S of n has n summation of n numbers, first n term, and we multiply the equation by r. And then the multiplication of r increase the power. And then we bring down the S of n being compared to r times S of n. And we can see they have many terms that seem common. And that means if we subtract them, we get rid of the uncertainty of those dot. Get rid of the uncertainty, we have a certain formula, a definite formula for the subtraction. So S of n minus r times S of n, the lower one minus the top one. We'll do this. And then many of the common terms get canceled. It's just 1 minus r to the power n that's left. So that's the proof of the formula for S of n. That's the actual formula for S of n instead of the one that in the text. So that applying this formula, it made it possible for us to get the total sum. When n goes to infinity, we have 1 over 1 minus r. Formula for the infinite sum in a geometric series. And we have this, apply that formula, we will have that this total sum, it will be 1 over 1 minus, and so this total sum equal to 2. So applying the formula of 1 over 1 minus r, we have a 2. Now, if we don't start from n equal to 0, if n equal to 0, 2 plus 0 equal to 1, that's the 1. But if we start from n equal to 1, we have this, right? So if we start from 1/2, 1/4 and keep adding it, you actually have to subtract the 1. If we only start from here, this total summation is equal to 1, even though if we start from 1, the total summation is 2. So our first example, we're starting from 1/2, that's why the total summation is 1, because we really didn't add the first one. Are we okay? So I have to kind of be careful with the impact of the first term. You start with n equal to 0, and this total summation actually equal to 2. But here, the summation, you start from n equal to 1. Start from n equal to 1, you have a smaller sum. Are we okay? So we know the difference between the 2 and 1. Yes? We okay? Right. So and we often have to double check what was the first term, because if you start with n equal to 2 or n equal to 1, you have less number term. And therefore, if you're applying formula, then you got to remember to subtract some of the initial terms. Anyway, this is a little exercise we already went through. Okay, and these are all geometric series. They have different r. And remember, to be convergent, r have to have the x value less than 1. That means the last one is divergent. Last one diverge. The first two converge because their common ratio is has an x value less than 1. So they converge. If they converge, we have to calculate the total sum. So applying the formula, the first one, the second one start from the first one. The first one start from n equal to 2, right? And the formula applies when you start from n equal to 0 equal to 4. But then that one start from 2, which means we have to minus the initial one, n equal to 0 or n equal to 1 has to be subtracted. So then we analyze, compare the two. That was the original formula applying geometric theory, and the bottom right is when a equal to 2 and start from 2. Subtract the first two terms. Any question? Okay, and then the second example, of course, start from n equal to 0, so 1 over 1 minus r. R is negative 1/2. That's all we need to calculate the total sum. All right, I guess this is the one, the part we stopped last time. We defined what's being called harmonic theory. Harmonic theory is a summation of 1 over n. 1 over 1, 1 over 2, 1 over 3, 1 over 4, all added together. The total sum is called harmonic theory. And the term harmonic is related to the study of music. that is special series. And number one, we're going to show this series is actually diverge. So how do we show it? A couple methods. I tried number one with number. I want to calculate 1 over n. So 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. I have 1 over n calculated out to 1 over 18. And you can see the number getting smaller and smaller. What about the summation? So if you only have one number, 1 plus 1 is 1. You have two number, 1 plus 0.5 is 1.5. Three number, the summation. So I write the summation on this column. And then what you can see is the summation is getting bigger and bigger. The rate of increasing is getting smaller. However, it's still increasing by the time I reach the 18th term. So that is the perception that this total sum are not approaching any number. So that's one way to determine or to say numerically the summation. I show the summation of the 18 number, but theoretically, even if you add one number to it, it's still going to be increasing. So the total summation is equal to infinity. Another way is actually show it. So here we have another approach. This is the proof given by the textbook. We're grouping the number together. So start with 1. There's 1/2, and then we can add these 3. 1 over 3, 1 over 4, 1 over. Okay, we're grouping 2 at a time, and then 8 at a time. Why do we do that? Because that's 2 to the power 1, and this is 2 to the power 2. So we're adding that many number. So if we have 1 over 3 plus 1 over 4, we relax it a little bit. 1 over 3 is bigger than 1 over 4. 1 over 4 plus 1 over 4 is 1 over half. 1/2. We have 1 plus 1/2 plus another 1/2. If we're adding 4 number in the whole sequence, then we stop at 1 over 8 at the bottom line. So 1 over 7 is also bigger than 1 over 8. 1 over 6 is also bigger than 23. So all 4 of them, 4 and 1 over 8 together is 1/2. So you can see the number in the whole sequence, if we relax, if we make it smaller, we see a lot of infinity 1/2. So we will have 1 plus 1/2 plus 1/2 plus 1/2 in the total summation. That kind of explains, if you add infinity 1/2, the total summation is infinity. There's what have it. Okay, so and then the one on the left, the one on the right, the smaller one, bigger or equal to, right? So this is a smaller one, smaller value is infinity 1/2, therefore it's infinity. Now this total summation is bigger than infinity, so itself is also infinity, and it's positive summation. If you add a bunch of positive numbers bigger than infinity, then itself has to be infinity. We have this conclusion that by comparison, if the total summation of the infinite number is bigger than infinity, of course itself would be infinity. And that's the mathematical proof of the divergence of the harmonic theory. Any question? So this, as far as proving the method of proof, it's kind of interesting to say that sometimes we change the number to a smaller side and it's still infinity. And that's one of the methods to prove when something is large, you relax this, make it smaller, and it's still infinity. That kind of method of proving something larger than infinity. Okay, so and that finished the proof, right? And then there's another theory we call alternating harmonic theory that is taking the harmonic theory, and then we change the sign and we make it positive, negative, positive, negative, positive, negative, which means in the original formula 1 over n, 1 over n is the formula for harmonic theory. In the original formula of the harmonic theory, we add a sign and alternating that. We multiply negative 1 to the power n plus 1. That's the factor we multiply that causes the term to alternate. And this is called alternating harmonic theory. Now this one actually diverge, meaning that if you add this many number, infinite many number, the total summation of this infinite number, it converges to natural log of 2. So the summation of the infinite number, total summation is actually natural log of 2. And we can confirm that. Number one, you can show this total summation. You take a partial sum. You can show that partial sum is actually I guess you stop at a positive number, like negative, like this. It's, it will be smaller than natural log of 2. Now, if you stop at a negative number, like from 1 to the positive 1/7, if you add it together, it will be bigger than natural log of 2. So you can see it's there. Sometimes the partial sum, sometimes is bigger than natural log of 2, sometimes it's less than natural log of 2. So it's alternating around that value and eventually converge to it. Hope that kind of makes sense because we're alternating. So of course it will be smaller than they compared to natural log of 2. But we'll proving it later when we actually have more method of handling the summation, the infinite sum. Okay, so now we're moving on to another kind of special theory. We use this one as an example. Let's say we want to find the total summation of this theory. And our common method so far is you're going to study the infinite sum. You will first study the partial sum. So we start with, okay, adding one number, 1/1 minus 1/2, and then we have 1/2. Adding 2 in the sequence, this is one term. One subtraction is one term. Okay, and then 1/1 minus 1/2 plus 1/2 minus 1/3. Then as of 2 is summation of 2 terms, we have 1 minus 1/3. As 3 is adding 3 number in that series. And you can see many of the middle terms are canceled, so the total summation is 1 minus 1/4. S of 4 is 1 minus 1/5. So what about S of n? Can you guess what was the formula? S of n equal to 1 minus 1/n plus 1. Yes. So it looks like S of n would equal to 1 minus 1/n plus 1. Just like S of 4 is 1 minus 1/5. So what about the relation between the index 4 and the number 5? Is 1/4 plus 1, right? That was the relation. So S of n is 1 minus 1/n. So the n plus 1 is comparing only the denominator that we observe with index that stay right next to the letter S. 1, 2, 3, 4. But here we have 2, 3, 4, 5. So you can see that adding 1 in the denominator. Right, so now we're going to make n go to infinity. N go to infinity, that is indicating S of n infinite summation. When n go to infinity, 1/n plus 1 go to 0. So that's really 1 minus 0. So the total summation actually equal to 1. So we realize that you add infinite many numbers here, the total summation actually equal to 1. It's understandable, right? You start with 1 plus 1/2. Minus 1/2 plus 1/2, minus 1/3 plus 1/3, minus 1/4 plus minus 1/5 plus 1/5, right? The minus plus all kind of cancel. So then the only thing that is not canceled is the first number, the 1. Any question? Total summation is 1 infinite sum. Okay, so we have this infinite sum series. Actually, it's 1. This we give it a special name. It's called a telescoping series. Theory in this example is called a telescoping series. What is a telescoping series? The telescoping series is one in which the partial sum reduced to just a finite number of terms. Now, when we see partial sum, right? So partial sum has more and more terms as you increase the index. S1 has 1 summation 1 number, S2 summation of 3 number, 2 number, S3 is summation of 5 number. So the number of terms will get more and more as you increase the index. That means that you end up having a uncertainty of number of terms in the total summation. But in a telescoping series, you are able to go to cancel many of the middle term, only a few terms left. You have finite number term for sure. You will have a formula for S of n if you have a telescoping series. So it's kind of like what happened with the telescope. I guess you're able to pull things from afar to really next to you. All the middle one is omitted because they were canceled. And being able to cancel the middle term is one of the main features for net telescoping theory. It allows us to study the partial sum in a more efficient way. Now, let's look at more telescoping theory to see what was the common method when we study this kind of examples. Here we have two examples. Start with example number one. Okay. So one of the things we have to do is how do we tell is a telescoping theory. One of the major things is you have to have a subtraction if you want to make it similar to a telescoping theory. So I want to figure out if there's any subtraction in the formula. The original formula of the theory does not have subtraction. So I am utilizing what we learned in section 6.4. That is to do a partial fraction decomposition. The 2 over n squared plus 2n is really 2 over n times n plus 2. So we're able to rewrite it. There's two factors in the denominator, the n and the n plus 2. So, and then there's a over n plus b over n plus 2. Right? That kind of method allows us to find the a, find the b. Because it's a 2 equal to a times n plus 2 plus b times n, right? If n equal to 0, we have 2 equal to, that was 0, this is 2 times a, so a equals 1, 1, and then 2 equal to, when n equals negative 2, we have b times negative 2, so that b equal to negative 1. Right? That's the process. It's really the partial fraction decomposition that we will follow if we were trying to determine it. So on the board, we already have it already decomposed into a subtraction of two fractions. The a is 1, the b is negative 1, the denominator is those two factors. And the factor of the denominator to be able to decompose the fraction. All right, we clearly see a subtraction now. So here we are. Once you are able to write it into a subtraction, then S1 is 1 minus 1 over 1 plus 2, 1 minus 1 over 3, and then S2 is 2 of these numbers subtracted. And we don't see any subtraction, so we end up having 4 numbers in the summation of S2. S3, we have 3 terms, and then we start subtracting cancel the 1 over 3. With the negative 1 over 3, and we have 4 terms as well. All right, S4, we got 1, 2, 3, 4, following the same formula for the partial decomposition. And we can cancel 1 over 3, cancel 1 over 4, and then we cannot do much. And then we still have left with 4 terms, and then S5 as well. And cancel 4 terms, we end up having 4 terms. Okay, so that was analyzing the partial sum. It's not very immediately available, but you can see some of the terms in there. Some of the terms are changing. You can kind of see vaguely some of the pattern. And I did this one, try to identify what was canceled. So I kind of circle around all the terms that was canceled, and then now on the right column, you see what's left over. Any questions? Are you okay? Kind of explaining the summation on the left. On the right is after canceling common terms, canceling the opposite terms. We have on the right. Any question? Want to make the combining the term that was opposite to a 0. All right, so we get this formula. So you can see ultimately in the end, the S of n is 4 term. Okay, and then we have a common term that's 1 and 1 over 2. And then we also have the remaining term that's related to the denominator, to the index n. And there's n plus 1, there's n plus 2 there. So now we have a way to handle summation. Any questions? So I'm just looking at what you have on the right as a way to identify the common formula. 3, 4, 4, 5, 5, 6, 6, 7, 7, 6, 7. Everything. Are you okay? So, I mean, imagine any difficulty if you see something that you don't quite understand. Alright, so now what we have a formula for f of n, we can find the limit when n go to infinity, the one that has n in the denominator, when n go to infinity, you have denominator going to infinity, the whole fraction approaching zero. The only two that's not approaching zero is one plus one half. These two fractions with denominator approaching infinity. They all approach zero. Any question? So now we actually have the answer of the total sum is 3/2. So this total summation, the final answer is 3/2. The major effort is trying to look at the partial sum and try to figure out if there is any pattern that we can summarize into a formula. So the formula for S of n is really important. If we don't have that one, we won't be able to find the limit of n to infinity. Then we won't be able to find summation. Any question? This is the first example. Everything that we calculated here involve an induction process of reasoning. You look at adding one number, two number, three number, four number in the theory. What kind of calculation we have. This kind of induction, you have to make sure when you analyze it, you write it nicely. So then when things are organized, it's easy to find the pattern when they're all messed up. When it's disorganized in the presentation, that's hard to find. It was a pattern, it's a trend. So we're gonna move on to the next example. So the second example, we have the natural log n plus 1 over n. So like we said, if you want to consider it being a telescoping theory, you have to have subtraction. The good thing is natural log, that logarithm of division is a subtraction. So number one thing is to understand the calculation. Natural log of n plus 1 over n actually equal to natural log of n plus 1 minus natural log of n. The formula is the law of logarithm. Which goes ln of a over b, it equal to ln of a minus ln of b. And natural, I think we said division inside the natural log is subtraction outside the natural log. Okay, so the number one thing is make some changes because without subtraction, we can hardly make it into a telescope theory. Any questions? And we're gonna apply that and start writing out the first few terms. I did S of 1. That's when you have only one term that's n equal to 1. So when you n equal to 1, it's natural log of 1 plus 1 minus natural log of 1. So we have natural log of 2 minus natural log of 1. Natural log of 1 equal to 0. So that's just natural log of 2. S of 2. S of 2 is adding the first two number. That's natural log of. I do the opposite. Natural log of 2 minus natural log of 1. Plus natural log of 3 minus natural log of 2, and then you can see the middle two get canceled. And also the natural log of 1 equal to 0, so then we end up having natural log of 3. S3 is adding first term, the second term, and the third term. S3 is adding 3 number, even though it looks like 6 number, because every term it is subtraction in itself. So adding all three subtraction, many of the middle term get canceled. On top of it, natural log of 1 actually equal to 0. So that's natural log of 4. So we start saying some pattern. All right, my question will be S of n, what is it equal to? What is S of n? I mean, we have S1, S2, S3. What's Sn? What's Sn?
Ln n minus ln 1.
Big L1 equal to 0, we don't have to minus. Actually, ln of S3 equal to ln 4, S2 equal to ln 3, S1 equal to ln 2. So Sn equal to ln n plus 1, right? Okay. So S of n actually equal to natural log of n plus 1. So if we want to find the limit, we like n go to infinity, natural log of infinity equal to infinity. It's a smaller, slightly smaller infinity, but it's infinity anyway. All right, so natural log of the infinity is still equal to infinity, therefore the natural log limit of SN is still equal to infinity. That means this total sum, this infinite sum equal to infinity. We have the infinite sum equal to infinity, so the theory actually diverged. And that's our second example. So as you can see, even though we have a method to handle telescoping theory, that doesn't mean what each telescoping theory equal to finite sum. You still have to work out the process, look at the partial sum, and see if the partial sum truly has limit. So telescoping theory only offered a possible formula to have a shorter formula of S of n. It made it easy to study the S of n, but it doesn't automatically conclude to a divergence or convergence. So divergent convergence still could be either way. Okay. Individual cases. This is the entire answer for the second example. Do you have any questions? So a special scenario that's what we call it. So this section is for the long. Right now, let's look at some of the property. And infinite sum is still a summation. So many of the rules for summation still apply. Rule number one: if you have these sequence multiply number. So inside summation, each term is multiplied by factor C. Now, as a rule, since we have summation of each term, every term has a common factor. The common factor can be brought outside the integration, outside of summation. So we mentioned this when we do integration. You have integration of a function times a number. The number is a coefficient. You can bring the number out of the integration just to make the calculation shorter. Same thing here. If you see a common number inside the multiplication, you can bring the number outside. Number just sitting there waiting for you to finish, and then you can work on the summation of less cumbersome terms. So this is one of the methods to shorten the calculation process. The second example is if you have summation, the infinite sum of a summation, you can actually turn them into two separate infinite sums. Okay. So infinite summation of addition equal to addition of the infinite sum. And that's the second rule. It doesn't apply to multiplication though. If you have summation of a multiplication, then it's not a multiplication of the infinite sum. So many of the distributive properties still applies, but multiplication is totally a different thing. Kind of like the integration. Occasionally I have students that are integrating this function times that function. And when you have integration of multiplication function, you have to apply. You could be applying integration by parts or substitution sometimes works. But you cannot do integration of this simpler formula multiplied by the other integration, right? So for example, if you want to integrate sine of x times e to the x, does the integration equal to integration of sine times integration of e to the x? It doesn't. Okay. So same thing over here. If you got an infinite sum of multiplication, you have to look at actually adding infinite number of multiplications. Okay, so we do have a couple of special theory, and even though the reasoning are not explained here, we'll probably explain it in 8.6 or 8.7 way later in the section. But now we bring them up just to make the calculation shorter. Number one is if you have a infinite sum of 1 over factorial, 1 over n factorial. Factorial is a large number, but if you put it in the denominator, then it's a small number. So 1 over n factorial is a small number. If you have an infinite sum of these small number, the full summation actually includes e. So this is another representation of e. And you all know that e is an irrational number. So we don't have a decimal representation, which is why we invented letter e. Say letter e represents this special number we often use in finances and engineering. So e is everywhere. E is on our calculator, but a traditional way to represent e is a limit. So e is a limit of 1 plus 1 over n to the power n when n go to infinity. It's actually a sequence e. Okay, and that's not a shorter way to represent it because you can use this as a way to calculate e. For example, you can just go 1 over 1,000. to the power 1,000. That's really roughly a way to calculate E instead of use a calculator to quickly get E without knowing that E is roughly 2.718, something like that. But this is another way to calculate it. You can also go 1/1, 1/2 factorial, 1/2, and plus 1/3. 3 factorial, 3 factorial is 1/6, and 4 factorial. So you can add a couple of factorial. Once you add enough factorial, you have a like almost exact number. That's another way to calculate it. And special sequence. Another special sequence is in the sum of 1/n squared, and this special sequence is pi squared over 6. One of the ways I remember this is there's an n squared, so there's a pi square. It's interesting to say when pi is involved in the calculation, see the original representation of the second series. There's no circle. Remember, pi is a number that we often have to use when circle is related. Circular region of all anything that's related to circle we have a pi. But right now, there's no circle, and then we don't have a background for the whole calculation. But that infinite sum equal to pi squared over 6 when pi involved in a numerical in the number theory study. All right, number 3 is also have an n squared, but we have alternating 1/n squared. So we have alternating sign. This is pi squared over 12. So that was pi squared over 6. This is pi squared over 12. So obviously the alternating sign causes the whole value to be smaller. Number 4 is alternating. Let's look at the alternating harmonic series. Harmonic series diverge, so you put infinity, but if you make it alternating, then that's a lot too. But however, you have an alternating the odd number in the denominator, it actually equal to pi over 4. And this is a more pervasive way to calculate pi. Another way to calculate pi, which does not involve square. That makes it easier for us to find the closer value of pi without have to look at a circle. Pi is a ratio between the circumference of the circle and the diameter of the circle. But this is a non-geometric way of studying pi. Anyway, these are all 6 formula. Number 5 is not a formula. So then there's only 5 formulas here. Actually quite a useful when you have special series in your calculation. You can show examples. All right, let's look at a couple of examples when this are being applied as rules. I'm not sure how much we remember them, but at least in the first one, it shows up. And number 2, sometimes you'll find it. The rest of them, I don't quite memorize at that well. So sometimes I have to look at my formula card to realize what exactly that was a special series, but what was the value for that series? I've got to look at a formula card myself. So memorization is really not the top list of my priority, but these are useful. All right, so let's look at a couple of examples when they are being applied. Then here we have 4 different examples. Those special series are being utilized when we do the calculation. So let's start with the first one. So this is what we observe right now. We realize this is the alternating series, and we already have a bunch of alternating series in this list. So I guess we'll apply number 3 very likely. Let's see what happened here. So when you look at the question number 1, number 1 thing is we have n squared minus n. When you have a fraction, n squared minus n is a subtraction in the fraction, so you can turn the big fraction into a subtraction of 2 small fractions. So number 1 will be utilizing a little bit algebra to rewrite it. I didn't really separate them into steps of the full solution here. So we start with n squared over n cubed minus n over n cubed. Start with break down the entire fraction into a subtraction of 2 small fractions. The reason we want to subtract them is that after you turn them into a smaller fraction, we can find common factors and cancel the common factors. For example, the first fraction, we have n squared cancel the n cubed, and you have 1 n left. So that is a alternating harmonic series. On the other hand, the second one, the n cancel the n cube, so we have n squared left. Both of these two are special theory that we have. This one is the alternating harmonic theory, and the convergence into a natural log of 2. Now this one is a alternating 1 over n squared theory. It converges to pi squared over 12. So all we have to do is apply the value that we have in that special formula. That's where the formula is being applied. So at first it looks like something that could be really complicated, but once we simplify it down, separate them into two separate series, then we can see that they fit into the formula that we already know. Any question? Next example is this one. It's 1000 over n factorial. 1000 is a common factor of all information. You bring that 1000 outside the series. Okay, now this one is 1 over n factorial. 1 over n factorial equal to e. But 1 over n factorial is when equal to 0. When n start from 0 for infinity. All right, so this is a summation start with n equal to 1, but the original formula n starts from 0. So when n equal to 0, 1 over 0 factorial is 1. So we don't have that term. That's why we have to subtract it. E minus 1 is because this summation, this infinite summation does not have that 1 at first. So we have a e minus 1 for the summation, and now it's the total answer to the question. Are we okay? Do you feel like is this too fast? Next example is a summation of 1 over 16 plus 1 over 25 plus 1 over 36. We realize that the denominator are squares. So like 4 square, 5 square, 6 square, 49 square, and infinite summation. So we have 1 over n squared exactly, but the n is 4. So 4 square, 5 square, 6 square, and 7 square, and keep going. So this is the infinite summation starts from n equal to 4, what it is. And but no matter what, whenever you have an infinite sum of 1 over n squared, we recall the formula that 1 over n squared, if you start from 1, then 1 over 1 squared, 1 over 2 squared, 1 over 3 squared. If you start from 1, this entire infinite summation is pi squared over 6. That was the formula from the formula page that we have in this file. So all we have to do is subtract. If we start from 4, that means we are not adding that many. So the first few terms are not in the whole summation. Therefore, all we have to do is subtract them. It's n equal to 1, 1 over 1 square, 1 over 2 square, 1 over 3 square. We get rid of it from the pi square over 6. That's the answer to this question. So if we don't have that many terms in the summation, all we have to do is subtract them. Any question? So you do see the difference between n equal to 1 and n equal to 4 as a starting point. So we okay. Right? So that's the total answer to the question. That's our third example. And then this one we do have to be careful with where do we start with the summation, like how many of them. We lose the first few terms if we change the first few terms. It's still going to be converged because we're adding 1 over n squared, but the total value of the summation is different. It's still convergent, but it's different. All right, number 5 is this one. We have summation of n squared over n factorial. The n factorial is n times n minus 1 times n minus 2. Keep going until 3 to 1 multiplied. So that's n factorial. So n factorial has n. N squared also have n. So we cancel the n. If the denominator is n times n minus 1 factorial, if you cancel the n, you have n minus 1 factorial, right? So that means we're able to cancel one of the n. So what do we do with the other n? We have a single way to rewrite it. So there's a little tricky treatment here. We can make this change because the denominator is 2 terms in the factorial. Let's try to make it 1 term. So we make the n minus 1 equal to m. So the denominator becomes m factorial. Now, if the n minus 1 equal to m, then m plus one equal to n, right? So the numerator n become m plus one. So numerator change to m plus one, denominator change to m. Also, if n equal to one minus one equal to zero. That means that m, because equal to n minus one, m starts from zero. So this change, that change. So we look at a different calculation there. The reason that we do this, because we also want to separate them and cancel more of the common factor. Any question? Right, so with that, notice that the variable, we use m for the variable. It's not required, it's not necessary to have to use a new variable. We can switch back to n as long as we make n equals from zero. So that one is what I added, because in the text, it goes directly from here to here. So it's like from n minus one, how do we go from those to n there? So m switch to the n, you can see everything is consistently the same. But without the change of variable, it's hard to trace back the reasoning. So I added this extra explanation to explain why this one is equal to this. So you have to switch to a new variable and then switch back, because representation of the variable, which letter do you use and stuff, it doesn't matter. What matters is the calculation. Any question? All right, so after we switch, we realize that this is a denominator and there's numerator, two of them. We separate the fraction. So n over n factorial is one fraction. 1 over n factorial is another fraction. So we switch this one theory to summation of two separate theory. And why do we switch them? Because after we switch them, we can cancel common factor. Because if you don't separate the summation, the n plus one is a factor, never have an n. So it's the reason that we write one theory into summation of two theory. Now we have common factor, the n cancel that n. Any question? Okay. All right, so now we have this summation infinite somewhat of 1 over n factorial, and we know that is e, right? Summation 1 over n factorial and from 0 to infinity, that's special number e. So this is already equal to, we know that summation already. For this one, we still don't know it. So how do we do it? We cancel common factor and we rewrite it. So the second summation is e already. The first one is summation of 1 over n minus 1 factorial. And we can do some more. And again, you can see if n minus 1 equal to m, n start from 1. So m actually starts from 0 because n equal to n minus 1. If n equal to 1, 1 minus 1 is 0. So m really starts from 0. But you see this one is summation of n factorial with n start from 0 to 1, which will be the same as 1 over n factorial with n from 0 to infinity. So anyway, this one also equal to e. So now we have it. So then we actually are looking at this two infinite sum, both of them equal to the number e. The total summation e plus e is 2e. So this is a final answer to this example. We're utilizing the e, the series representation of e. So we have a limit representation of e. We have a series representation of e. So there's a different way to represent e. You can be represented too. But the rate of conversions might be a little bit different. Any question?
Yeah, could you explain on the second line again, how,
This one?
yes, how it went from n equals 0 to n equals 1? In the sum?
It's in here. So, so from here, the denominator have two, like a subtraction n minus 1, which made it hard to cancel common factor. So what we can do is we switch to a new variable. We do a substitution variable. M equal to n minus 1. So denominator become n factorial. And then if you have m equal to n minus 1, adding a 1 on both side equation, then n equal to m plus 1. So that m equal to, the n in the numerator equal to m plus 1. We okay?
Sorry, in the summation where n equals 0 to infinity to n equals 1 to infinity.
N equal to 1, there's m is n minus 1. If n equal to 1, m will equal to 0. Isn't that? If m equal to n minus 1, if n equal to 1, n equal to 1, then m equal to 0. That's the starting point.
I think it means the line down where it goes from n equals 0 to n equals 1.
Oh, from here to here.
Yes.
It's because it's because when n equal to 0, the numerator will be 0 divided by 0 factorial. 0 factorial is 1, but the 0 over 0 factorial equal to 0. So then when n equal to 0, because it's equal to 0, it doesn't really have any value. So then what it actually starting is from 1. You're saying when n equal to 0, it doesn't really have any value in the summation. N equal to 0 or equal to 1 would be the same, but it's not the same if you switch the cancel the common factor, it would be the same. But if you still have the n equal to 0, 0 minus 1 factorial is undefined. So if you cancel the common factor n, we're forced to move on and remove the n equal to 0 term. In the original summation in the middle, n equal to 0 doesn't matter because you put a 0 value in the summation, but it matters here.
Yep.
You okay? So here we can't have an n equal to 0 there. And also because we already canceled the n there. So n equal to 0 is no longer 0. So you have to remove that. I kind of see what you from n equal to 0 to n equal to 1 there. In the middle of the second line, if n equal to 0, the value equal to 0. So we could remove n equal to 0 right there. Any other questions? So it's kind of interesting way to prove the final answer. But of course, because we're adding infinite sum, there's always a numerical way to do it. So when you are handling a theory in actual calculation or exam, if you really are in a rush and can't figure out the algebraic method, what you can do is use numbers. So you can just go from n, if you have a quick calculator, if you add from n equal to 1 to n equal to 10, if you add 10 number in the whole series, because it converged, you probably are getting quite close to the truth. You know what I'm saying? Because it's a summation of infinite number. It's impossible to add infinite number by hand, but it's possible to add 10 or 12. And if it converged, it will start looking really, really close together. So as long as you add enough number, you're getting almost the exact number if it converge. If it diverges, then it's a different thing. Then we might not be able to numerically calculate it, but as long as it converge, we can always use numbers. Any other questions? Okay, let's see. Now, the rest of the pages are some of the special attention. Number one thing is if you have a convergence theory, that means the total, the summation of the infinite number. If they converge, that means the infinite summation, infinite number added together equal to a finite number. So as a consequence, every single number has to be really, really small. How do we represent small? It means that individual number has to have 0 as its final limit. You can see that from every example that we observe. This is a really small number, especially when n is big. So it's almost 0 and n equal to like 10, n equal to 10. 10 squared over 10 factorial, this is a really, really small number. And you can see all these numbers for every sequence that realize these are multiple pages. So one of the number one thing, if the whole thing equal to a finite sum, and in the infinite sum equal to a finite number, then individual term has to have limit equal to 0. As a consequence, if the individual term does not equal to a limit of 0, that means every individual term is not small enough. And then that means the whole summation are going to be infinity. So the summation of the infinite number, when each number are not approaching 0, the total summation is going to be infinity. And that's we say the theory will diverge. So if you have a convergence infinite theory, the individual term have the limit 0. If the individual term limit is not 0, it's guaranteed that the whole theory will diverge. So that's how heavily put into individual terms to be a super small number. Another one is, we've been doing this, quite well. That is the first few term, maybe 4, maybe 2, maybe 5, maybe 10. You can get rid of it. The converge or diverges depend on infinite sum. So it's all the term after that really matters. So the first 5 or first 3 or first 2, if you remove it or add it to it, it doesn't affect the converge diverge facts. It might change the value if it diverge, but it doesn't change the fact of converge. So number one, if you have a divergence theory, then adding or subtracting a few number in the whole theory, it will still be diverged because really the infinite many number is what's causing it to diverge. The second one is if you have a convergence theory, it will remain convergent if you add or subtract a few number in the whole list. If you set convergent, the value will change. But the actual converge facts will be stay the same. Any question? And we're just saying the first few number. If we are calculating the exact number, then the first few terms are really important because the first few term is the largest number. For its convergence theory, all the other numbers, for higher n values, but the number are really small, the first few number are the larger number. But for the convergence, divergence, what really matters is overall tendency. This is just saying how less important the finite terms is with respect to diverge or converge of the theory. Right, this is the end of the 8.2. The homework has already been assigned. I hope that we can try them to see if we understand the ideas. Let's see if we have time to go through a couple of examples. This one's the Right, the question in this assignment are, right, so some of the questions ask you to calculate final sum. For example, S2, is that in the first two number? You kind of understand what do we mean by partial sum. So S2 is adding 2 number in the list. Okay, S4 will be adding 4 number. I really have not worked out the process. You just add them, but using your calculator, S4 is adding the first 4 number, S6 is adding 6 number. Just keep writing the pattern, fixing what we are adding. This is the terminology for the partial sum. Question number 1. Question 2 is to determine converge or diverge. And I give you a question. Is this one diverge or converge? Do you see the limit? What's the limit? It's 1, right? That means every single number is roughly 1. If you're adding infinite many of 1, what's the total summation? No, it's infinity, right? It's 1 plus 1 plus 1 plus 1. You are adding infinite many. So the limit of the individual fraction is 1. But if we're adding infinite many numbers here, so it goes 1 over 10 and 2 over 11. And if you keep adding, they're getting bigger and bigger. So this will diverge. It looks like we're out of time. Try to see if our exercise helps. And tomorrow I'm going to move on to 8.3. That's it. Thank you. I'm passing out the exam. You need your exam back. Or if you have the flicker question.
Yeah.
Yeah.
The flicker question we sorry.
Wait, what do you mean?
My cousin.
She put it
Okay.
Oh, I was just rearranging things. Because I have it in my pocket. So I don't like. Or it'll get so.
Henry can see.